Alright, so welcome back to part 6 of thermal physics. I'm starting to lose count, so please forgive me if I call the wrong number today. Okay, so we're on to specific heat capacity, and what I wanted to look at are the 6 main equations that we're going to be using to calculate specific heat capacity. Well, not to calculate specific heat capacity, but in which specific heat capacity will be used to calculate heat loss or heat gain. Now, what is specific heat capacity? Specific heat capacity, which has the symbol of C, of a substance is the heat required to produce unit temperature rise in unit mass. Heat, like other forms of energy, is measured in joules, and the unit of specific heat capacity is joules per kilogram per degree Celsius or joules per kilogram per Kelvin. And you see how they can be written. You could write them with the slash, or you could write them with the negative ones. This is much preferred though. Most scientists prefer this one and this one. Most examining bodies. However, when you use this one, you're able to do your calculations nicely. In physics, the word specific means that unit mass is being considered. Now, how do you calculate the heat? How do you calculate heat loss or heat gain? You use this very nifty equation where you multiply mass by the temperature change by the specific heat capacity. Note well that the specific heat capacity is not the same for all substances, hence the word specific. And also we're dealing with unit mass, usually either 1 kilogram or 1 kilogram at 1 degree Celsius or 1 gram at 1 degree Celsius. Okay, the units for mass are in kilograms. The unit for temperature is going to be either in kelvins or degrees Celsius. Well, going to be in either kelvins or degrees Celsius, and the unit for specific heat capacity is either joules, joules per kilogram degrees Celsius or joules per kilogram Kelvin or joules per gram degrees Celsius or joules per gram per Kelvin, and that depends on whether you're using kilogram. In this case, because this is kilograms here, you would either use this one or this one. If this were in grams, then you would use joules per gram degrees Celsius or joules per gram Kelvin. Okay? Alright. Now here we have a question. It says, if the temperature of a 5 kilogram mass of copper of specific heat capacity 400 joules per kilogram degrees Celsius rises from 15 to 25 degrees Celsius, what is the heat received? Alright, so we're going to start listing the things we have. We have mass, we have specific heat capacity, and we definitely have a temperature change. Right, so we're going to write the mass here, which is 5 kilograms. The temperature change is usually T final minus T initial. And in this case, the final temperature is 25 degrees Celsius and the initial is 15, and that will give us 10. And then we have the specific heat capacity of the copper, which is 400 joules per kilogram degrees Celsius. They said heat received. We know it's heat received because the value for temperature change is positive, so that's how we know it's heat received. So EH will be equal to mass times specific heat capacity times temperature change. And if you look at this, this is like MCAT. So if you can't remember, just say MCAT. And so we're going to substitute now. The mass is 5 kilograms. And C, specific heat capacity, is 400 joules per kilogram degrees Celsius times 10 degrees Celsius. You could start cancelling some units to make your life easier, and you will notice that you're on the correct track because the unit of heat is actually joules. Now if you start to multiply, you're multiplying here. 5 times 400 times 10, you get 20,000 joules. And if you want to write that smaller, you get rid of these 3 zeros, 20 kilojoules. Alright, so that's the answer for this question. Now, thermal capacity, on the other hand, it deals with the quantity of heat needed to raise the temperature of the whole body by 1 degree Celsius, so it's the entire body. So it's no longer just 1 kilogram or 1 gram, it's the entire body. And how you calculate that is by multiplying the mass of the substance by its specific heat capacity. The units for thermal capacity is joules per degree Celsius or joules per Kelvin. Now here we have, we could try this question for a copper block of mass 0.1 kilogram and specific heat capacity 390 joules per kilogram degree Celsius. What is the thermal capacity? So let's go on to our worksheet. I'm gonna use yellow now because yellow is nice and bright. And we're going to list all the things we have. We have mass. Always list, by the way, because then you don't forget anything. So we're going to put the mass right here, equal to 0.1 kilograms. And we're going to put the specific heat capacity. So if you notice, you have to remember the symbols, right? It's 390 joules per kilogram degrees Celsius. And remember, thermal capacity is equal to C equals to mass times specific heat capacity. We have the mass, and the specific heat capacity is 390 joules per kilograms degrees Celsius. If we multiply this, we get 39, and we have to take care of our units. We get 39 joules per degree Celsius. Great. So I hope everybody got that. Now let's try these questions together. So these are now questions that refer to specific heat capacity and the 5 equations that were given at the beginning. So here we have equation 1. Here we have equation 1. EH is equal to MCAT. That's the original one. Do note that EH is also equal to potential energy, and EH is also equal to kinetic energy because the two of these actually give off heat. Remember, when work is done, heat is always given off. That is the relationship. So with potential energy, we know that potential energy is equal to mgh. So therefore, EH will be equal to mgh at some point. And remember that kinetic energy is equal to mass times the square of velocity divided by 2. So EH would also be equal to mass times velocity squared over 2. EH is also equal to power times time. EH is also equal to mass times latent heat of fusion. and EH is also equal to mass times latent heat of vaporization. So here we have a question. A tank holding 60 kilograms of water is heated by a 3 kilowatt electric immersion heater. If the specific heat capacity of water is 4200 joules per kilogram per degree Celsius, estimate the time for the temperature to rise from 10 degrees Celsius to 60 degrees Celsius. Please note that 1 kilowatt is equal to 1000 watts, which is also equivalent to 1000 joules per second. So this should be 1000, can you see? Yes, this should be 1000 joules per second. And we let T be the time taken in seconds to raise the temperature of the water by 60 minus 10 degrees Celsius, which is 50 degrees Celsius. Therefore, heat supplied to water in time will be T equal to something. Alright, so that was a mouthful. Now, in the spare time, pause this slide or pause this part of the video and please write down all 5 equations. They're also here, so you should write them down. Now let's try this. We have a mass of 60 kilograms, and I know this is mass because the unit, the SI unit for mass is kilograms. So we have the mass, which is 60 kilograms. And we have the power. We know this is power because we see watts right here. So we know this is power. This is mass. And so the ways you could find out what these values are, remember we learned in chapter 1, the value of a number is just not, you just calling a number, you know, it would never give you what the quantity is being measured. So if I just say 60, what's the quantity related to? What is the quantity? So now we know that this is power because of the units. So you always have to have the units. So power is equal to 3 kW, which is actually 3000 watts, which is actually 3000 joules per second. If the specific heat capacity of water is 4200 joules per kilogram degrees Celsius, estimate the time for the temperature. So that's what we're looking for. So we have this, which is C. Estimate the time for the temperature to rise from 10 to 60. So we have initial temperature, which is 10 degrees Celsius, to final temperature, which is 60 degrees Celsius. So delta T would be 60 minus 10, which is at 50 degrees Celsius. So looking at these equations, which one would you use? Which one has P in it? Correct, equation 5. So we're using EH equal to PT. And that will give us, if EH is equal to MCAT, we could say MC delta T is equal to PT, right? And so since we're looking for temperature, for time, we're going to solve for T. So we're going to divide both sides by P. We're writing this to make sense because we read from left to right. What we're going to do is put MCAT on the right hand side over P. Then we're going to start to substitute. So the mass is 60 kilograms. C is 4200 joules per kilogram degrees Celsius, and delta T is 50 degrees Celsius over power. So the power we worked out was 3000 joules per second. Now if we take all of these units out here, we have kg times J over kg degrees Celsius times degrees Celsius. So we can put this over 1 over J over S. We get we start to divide up here and we end up with J over S. that gives us J times S over J, because remember it flips. The J's cancel out, so our answer will have units of seconds. So we could start to cancel out our zeros, and we start to multiply now. So we said that times 42 times 50 times, divided by 3 should give us 4200. So 4200 seconds. Wow. Right? So 4200 seconds. I hope you got that. Let me redo the calculation to make sure that I did it correctly. Okay, great. Alright, so this is another one. A piece of aluminum of mass 0.5 kilograms is heated to 100 degrees Celsius and then placed in 0.4 kilograms of water at 10 degrees Celsius. If the resulting temperature of the water is 30 degrees Celsius, what is the specific heat capacity of aluminum if that of water is 4200 joules per kilogram per degree Celsius? Here, heat given out by the aluminum is heat taken in by the water. So, the piece of aluminum is heated. So, if we draw up a setting like this, we have aluminum in here, in some water, a flame underneath it, and it's heated. What happens next is that you have a cup, a styrofoam cup, and the aluminum is placed in here. Some heat loss to the surroundings, but that's ignored. So that's put in here, and the temperature of the water was registered earlier, the initial temperature, right? So when this aluminum is put into here, eventually they're going to equilibrate out. They're going to reach to some thermal equilibrium, right? And so this will be the final temperature for both the aluminum and the water. That's pretty much what's happening. So we're going to list these out under their respective columns. And the mass of the aluminum was 0.5 kilograms. And it was heated to 100 degrees Celsius, so that's the initial temperature. And then placed in 0.4 kilograms of water. So the mass of the water is 0.4 kilograms. And the initial temperature of the water was 10 degrees Celsius. If the resulting temperature of the mixture is 30, so the final temperature of both will be 30 degrees. What is the specific heat capacity of aluminum if that of water is 4200 joules per kilogram degrees Celsius? Now here we're going to equate them and say the heat given out by the aluminum will be equal to the heat most definitely gained by the water. So remember, heat moves from hotter bodies to colder ones. So remember, we learned that earlier. So since we know what EH is equal to, we're going to say MCAT of aluminum, right, would be equal to the MCAT of water. Now before we start substituting, we're going to solve for delta T for both of them. So for delta T for this one is final minus initial. So 30 minus 100. would tell us that you have negative 70. You don't have to carry the negative sign in here. Okay, this just indicates that heat was lost, this negative sign. And then delta T for this one will be 30 degrees minus 10 degrees Celsius. And that will give us 20 degrees Celsius. And this tells us that heat was gained by the water, right? Because it's positive. And now we could start transposing. So we're looking for the C of aluminum. So because we're looking for C of aluminum, we got to get rid of the mass and the delta T. So mass of aluminum and delta T of aluminum, and we divide this side by the mass of aluminum and the delta T of aluminum. Right? So this cancels out, and now we see that C delta aluminum is equal to what is the mass of water. The mass of water is 0.4 kilograms. C is 4200 joules per kilogram degree Celsius, and delta T of water is 20 degrees Celsius. And the mass of aluminum is 0.5 kilograms, and the delta T of aluminum is 70. So remember, we don't put the negative sign because the specific capacity is not going to be a negative number. Okay, it's just to indicate that, well, heat was lost. Now if we calculate this, you realize we get rid of some units first, and we're pretty good. We're going to get back the same units of joules per kilogram degree Celsius, because that's the units of specific heat capacity anyway. And you calculate this, you get 960. Right? So I'm going to put the units a little bit closer. And that's what you will get for this particular answer. So again, the aluminum was heated up in some water to 100 degrees. It was removed and placed into another set of water to determine its specific heat capacity. We call this method of mixtures, right? And then eventually reach the thermal equilibrium where both would have been the same temperature. Why we boil the metal is because that is an easier way of heating up the metal and getting a temperature. And because of thermal equilibrium, we know whatever temperature we get in the water will be the same temperature as the metal. Okay? Okay, so I hope you understand that one. You could always pause the video and try to do this all by yourself to the point where there was nothing underneath here. Okay? Okay, so the importance of the high specific heat capacity of water. The specific heat capacity of water is 4200 joules per kilogram degree Celsius, as you saw on the previous slide, and that of soil is about 800 joules per kilogram degree Celsius. As a result, the temperature of the sea rises and falls more slowly than that of the land. And you would have experienced this if you live on an island. You experience this all the time when you go to the beach. The sand is so hot when you're there and the sun is pelting and you just say, whoo, ah, 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 because you want to get in the water, which is cool, and it's so cool and the sun is so hot. So again, water takes a long time to heat up. A certain mass of water needs 5 times more heat for its temperature to rise by 1 degree Celsius than does the same mass of soil. And if you look at that, if you divide 4200 by 800, you're going to realize it's the truth. So divide that and you will get 5.25, right? Water also has to give out more heat for its temperature to fall by 1 degree Celsius. So again, it goes back to the fact that the temperature of C Water rises and falls more slowly than that of the land. Since islands are surrounded by water, they therefore experience much smaller changes of temperature from summer to winter than do large masses such as Central Asia. Now, potential energy, conversion of mechanical energy to heat. The potential energy of water at the top of a waterfall becomes dash energy as the water falls. So yes, correct, it becomes kinetic energy. And when it strikes the ground, heat and dash are produced. Yep, heat and sound. You could hear a waterfall falling before you even find it. So the temperature of the water at the bottom is higher than that at the top. If you assume that all the potential energy becomes heat, the temperature rise can be calculated. So in this case, we're going to be using EH equal to EP because it involves potential energy, right? So as you can see here, they have EH equal to EP, where EH is actually MCAT and EP is actually MGH. When you transpose, if you're solving for, what is solving for? This, consider 1 kilogram of water falling a vertical distance of 105 meters. So we have the mass of 1 kilogram and we have the height of 105 meters, and we know that the specific heat capacity of water, because we're dealing with water, is 4200 joules per kilogram degrees Celsius, right? And if we have MCAT equal to MGH, and we're looking for, we have mass, we have height, we have gravity. So we're looking for temperature change, and we're going to take gravity to be equal to 10 newtons per kilogram. What we will find is that we're going to start dividing. So we're going to divide this side by mass and specific heat capacity, and we're going to divide this side by mass and specific heat capacity. So that goes. So we end up with delta T equal to the mass times the gravity times the height over mass and specific heat capacity. But because we're dealing with the same mass, that goes. So you're going to end up saying gravity times height over specific heat capacity. And since the gravity is 10 newtons per kilogram and the height is 105 meters over 4200 joules per kilogram degrees Celsius, we start to calculate now. So we say 10 times 105, 1050 divided by 4200, and that gives us 0.25 degrees Celsius. That would be the temperature change. Now, kinetic energy. When a car is brought to rest by the brakes, kinetic energy becomes heat and the temperature of the brake linings or disc pads rises. Now, all of this is just saying that anytime you exert energy in any form, potential, whether it be potential, kinetic, work, because power is actually work, whether it is in any of those forms, just note that heat will be given off, and that's why you can relate all of these equations to heat being given off. That's basically it. Now remember we explored caloric theory and we found out why the caloric theory was obsolete, and it was simply because they couldn't prove that caloric existed. They couldn't prove it because they realized that when something was hot, it did not have a different mass to when it was cold. One. Number two, if caloric was an invisible fluid, it should have been able to come out of one body and totally enter another body, and that body that it came out of was supposed to get cold while this body gets hotter, right? So that was the base means why caloric theory was made obsolete. Okay? Now here are some scientists that proved or brought up will cause it to become obsolete. Their findings caused the theory of caloric to become obsolete. So here we introduce Rumford. The evidence against the caloric theory came from observations Rumford made while supervising the boring of brass cannons at the military arsenal in Munich. Now, boring is a machining process which is used to enlarge the diameter of a hole in a metallic object by using a cutting tool. In those days they used horses, right? In this procedure, the cutting tool is used to cut the metal off the hole, which is rotating at a very high speed. Because horses, they didn't have machines like machines that could work without animals. They weren't technologically advanced yet. Horses proved to be the next best thing. Okay, as you can see here, and so they have some grooves in here, and as the horse moves, it causes a turning effect to make a hole in the cannon itself, and you can see the metal being shaved out, right? Now, from just this simple observation, he realized that how hot both the cannons and the brass borings became. Moreover, the effect continued for as long as the boring did. It seemed to Rumford that one, heat can be created and so is not a material substance, and he also realized that it is created when work is done against friction, which is an opposing force, as it is in boring a cannon. That is, mechanical energy and heat must be related. So he came up with that observation. The caloric theory was not overturned until the mid-19th century, largely through the work of the English brewer and amateur scientist Joule. We realized that these people were not really into science, they were just doing their thing on the side. And these were all observations that they put in, and they realized something was wrong with what the scientists of the day were saying. So basically, Joule discovered the amount of work that had to be put into raising 1 kilogram of water to 1 degree Celsius by using a closed system, a mass, and a paddle wheel, as you can see here. It was very crude. The setup was very crude. On all occasions, Joule found that a certain amount of mechanical energy always produced the same amount of heat. This is the rate of exchange between them. That is the rate of exchange between them was fixed. Around the same time, the view that matter consists of atoms and molecules was gaining ground and helped to make more plausible the opinion of Joule and others that heat was a form of energy connected with molecular motion. Today, we believe that when matter is heated and its temperature rises, then this is due to the speed and to the kinetic energy of the molecules increasing. Joule's work also helped to establish the conservation principle for all forms of energy. And that is the conservation of energy. The conservation of energy states that energy cannot be created or destroyed. It can only be transformed from one form into another. And here we have some questions which we're going to tackle now. So here we have some questions. 1, 2, 3, 4. How much heat is given out when an iron ball of mass 2 kilograms and specific heat capacity 440 joules per kilogram degree Celsius cools from 300 to 200 degrees? So we want to know how much heat is given out. We're gonna list. So mass is 2 kilograms. Specific heat capacity is 440 joules per kilogram degree Celsius, and initial temperature is 300 degrees Celsius. Final temperature is 200 degrees Celsius. So delta T would be 200 minus 300 degrees Celsius, which is negative 100 degrees Celsius. So this tells us that heat was given off. Definitely heat is given out. It's negative. And so we have the mass. So EH will be equal to MCAT. The mass being 2 kilograms, the specific heat capacity being 440 joules per kilogram degree Celsius, and the temperature change being 100 degrees Celsius. Again, we don't put the negative sign because it's understood that heat is being given off. And that gives us a whopping 88,000 joules. These cancel out. Okay? So again, you could try these questions by yourself, and then or you could work along with me. You could do anything you want. You could watch me do it first, and then you could do it next, whatever you want. But if you want to do it first, you could pause it, do it, and then come back to it. How much heat is needed to raise the temperature by 10 degrees Celsius of 5 kilograms of a substance of specific heat capacity 300 joules per kilogram per degree Celsius? So how much heat is needed to raise the temperature? Okay. So we're looking at the temperature change. Delta T is already calculated for us. The mass is 5 kilograms, and the specific heat capacity is 300 joules per kilogram degree Celsius. So we have the CAT, we have the MCAT. So we're going to say EH is equal to MCAT. So the mass is 5 kilograms. C is 300 joules per kilogram degree Celsius. And the temperature change, which is already calculated for us, just goes in there naturally. And if you calculate this, you get 15,000 joules. Okay. Alright, so 2,000 joules of energy is needed to heat 1 kilogram of paraffin through 1 degree Celsius. How much heat is needed to heat 0.5 kilograms of paraffin through 8 degrees Celsius? So we're dealing with the same material, okay? So we're going to say paraffin 1 and paraffin 2. So in the scenario with paraffin 1, we have EH equal to 2,000 joules, and we have the mass equal to 1 kilogram, and we have the temperature change, which is 1 degree Celsius. And then with paraffin 2, it says how much heat, so we're looking for EH. EH equal X, and then we have the mass 0.5 I have the temperature change, which is 8 degrees Celsius. They didn't give us C because it doesn't matter. If the two of them have the same specific heat capacity, they're going to cancel out. So we're going to say EH of P1 will be equal to the EH of P2. Okay? Well, let's first work out. I'm going to show you why. Let me see. So let's work out the specific heat capacity of P1. Let's do that. So we have EH of P1 equal to MP1 specific heat capacity P1 and delta T of P1. We're trying to solve for C, so we can divide both sides by MP1 and delta T P1. And since you read from left to right, we're gonna put C P1 equal to the EH, which is 2000 joules, the mass, which is 1 kilogram, and then the temperature change is 1 degree Celsius, and that will give us 2000 joules per kilogram degree Celsius. So now we know what the specific heat capacity is. I can put it over here, and now we could solve the heat needed. So it did indeed need it. So my bad, sorry about that. So now we're gonna solve for EH of P2. So EH P2 is equal to M P2 times C P2 times delta T P2. And we don't have to transpose anything because everything is already set. So the mass of P2 is 0.5 kilograms and C is 2000 joules per kilogram degree Celsius, and the temperature change is 8. Now you calculate that and you get that's 8,000. Joules. Okay. How many joules of heat energy are supplied by a 2 kilowatt heater in 10 seconds and 1 minute? So let me just change this to 60 seconds one time. So because we're dealing with time, we know we're going to be dealing with EH equal to power times time. Let me change this color to something else, maybe red. So in this case, in A, we have T equal to 10 seconds, and we have P equal to 2000 joules per second. And in B, we have T equals to 60 seconds, and P equal to 2000 joules per second. So EH will be equal to 10 seconds times 2000 joules per second, which will give us 20,000 joules. And then EH will be equal to 60 seconds times 2000 joules per second, and that will give us 120,000. I'm just making sure 120,000 indeed. joules. Okay, if you want, you could write these shorter, 20 kilojoules, and this one it was 120 kilojoules. So the more time you spend, the more heat you're going to be given off. Okay, so I hope you understood those questions, and now we have the last 3 questions for this topic. When 0.1 kilograms of a metal at 100 degrees Celsius is dropped into 0.15 kilograms of water at 25 degrees Celsius, the final temperature is 30 degrees Celsius. What's the specific heat capacity of the metal? So we're going to do metal. This is again mixtures of metal. When you see metal drop into some water, it's always method of mixtures. Where they take the metal, boil it in water, and take the hot metal and put it in another set of water. So whenever, that's how come I know. Whenever you see that, boom. That's what the question asking you. So the mass of the metal is 0.1 kilograms. Initial temperature is 100 degrees Celsius. Final temperature is 30, because it's the final temperature is 30. And we're looking for the specific heat capacity of that metal. Now the mass of the water is 0.15 kilograms. The initial temperature is 25 degrees Celsius. The final temperature is 30. And the specific heat capacity of water is actually 4200. Now if we equate the two, metal equal to EH, water, then we have M and C and delta Tm equal to M water, C water, delta T water, right? And we're looking for the specific heat capacity of the metal, so we're going to divide both sides by this. So cancel out. So C equals to the mass of the water, which is 0.15 kilograms. The specific heat capacity of the water, and then the temperature change of the water. We didn't work that out, which would be 5. So 5 degrees Celsius. And then the mass of the metal underneath is 0.1 kilogram times 70. Notice we don't have negative 70, but again, we don't deal with that because it's just an indication that heat was lost. So if you work this out, we should get $450. Hope you got that. So 450 joules kilogram degree Celsius, because this goes, this goes, this goes, this goes, and that's what's left underneath. Okay. So an electric water, so once you heat electric, you know there's power involved. An electric water heater raises temperature of 0.5 kilograms of water by 30 degrees Celsius every minute. Assuming that no heat is lost, what is the power of the heater? What's the power of the heater? So here we're going to do this. The mass equal to 0.5 kilograms. The temperature change is 30 degrees Celsius. And the time is 60 seconds because I said every minute. So Assuming that no heat is lost, what is the power of the heater? So if EH equal to PT, we could switch it around so that it makes sense to us. And we're searching for the power, we're going to divide both sides by T. Right? We're dealing with water, so the specific heat capacity of the water will be 4200 joules per kilogram degree Celsius. So since we have this, we know P is equal to MCAT, because EH is MCAT, over time. Filling that in, P equal to the mass, 0.5 kilograms, times 4200 joules per kilogram degree Celsius, times 30, divided by the time, which is 60 seconds. So those cancel out right there. So we calculate 0.5 times 4200 times 30 divided by 60, that's 1050. So you have power equal to 1050 joules per second, which is equivalent to 1050 watts. A watt mass of cold water at 20 degrees Celsius must be added to 60 kilograms of water, hot water at 80 degrees Celsius by someone who wants to have a bath at 50 degrees Celsius. Neglect heat losses. Well, this seems fun. Let's show you how much. Okay, so we have cold water and we have hot water. So we have the initial temperature of the cold water being 20 degrees Celsius, the final temperature being 50 degrees Celsius. That's what I want to know. Hot water has an initial temperature of 80 degrees Celsius, and the final temperature for that should be 50 degrees Celsius. C would be 4200 because it's water. And then they want to know what mass of cold water. Did they have a mass for hot? Right, so they have a mass for hot, which is 60 kilograms. Okay, so we're going to just equate EH cold water, and why I put cold water first is because that's the missing thing right there. It's easier. So EH hot water. So we're gonna have that, and delta T cold water, and then this hot water, C hot water, delta T hot water. Now we're solving for the mass of cold water, so we're going to divide each side by C and delta T on both sides. C delta T. Now these cancel out. Now if you realize both of them have the same C, so we're going to just cancel out that to make our work easier. And the mass of the hot water is 60 kilograms, and the temperature change would be 30. The temperature change of the cold water would be 30 as well. Yeah. And you realize that it's gonna be the same mass of cold water. Right? So I hope this helped, and so we're gonna move on to part 7, I think. I'm not even sure now. We're gonna move on to specific latent heat at another date. Have a good night, folks. enjoy. I hope I helped. I hope I was able to help. Bye.